Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss plane electromagnetic waves through isotropic dielectric medium. Let's begin. Here, we derive the expression for electric field and magnetic field intensity when plane electromagnetic waves propagates through isotropic dielectric medium. That medium is isotropic. Isotropic means direction independent. If we measure a physical quantity in case of isotropic medium, then that physical quantity's value is same in all directions. That's why that medium is called isotropic medium. Basic condition for non-conducting isotropic medium. Non-conducting isotropic medium the conditions sigma, that is conductivity 0 since we consider non-conducting, rho charge density also 0, no source of charge, and the expression for displacement electric current vector D vector epsilon E vector epsilon is the permittivity of that of medium that responds to charge. B vector is equal to mu H vector, mu permeability that responds to that magnetic field, and here current density J is equal to 0. These are the conditions for non-conducting isotropic medium. Here we derive the expression for electric field and magnetic field when that plane waves propagating through that of isotropic dielectric medium by using Maxwell's equations. From Maxwell's equations, Maxwell's first equation grad dot D is equal to rho. We have used the conditions or grad dot D as epsilon E rho 0 or grad dot E is equal to 0. Equation number 1. Next equation grad dot B is equal to 0. Grad dot B is equal to 0 or in place of B mu H, grad dot mu H is equal to 0, grad dot H vector is equal to 0. Equation number 2. Next equation number 3, as grad cross E vector is equal to minus del B by del T. Grad cross E vector is equal to minus del by del T in place of B mu S vector. Grad cross E is equal to minus mu del S by del T. Equation number 3. Last Maxwell's equation, grad cross H is equal to J plus del D by del T. Grad cross H, J is equal to 0, del by del T, D epsilon E. Grad cross H is equal to epsilon del E by del T. Equation number 4. 4 Maxwell's equations are now changed under that of condition for non-conducting isotropic medium. In order to calculate the wave equation, we have to calculate for electric field and magnetic field. Therefore, taking call on both sides of equation number 3, we can easily get the expression in terms of E, and again call on both sides of equation number 4, we will get the expression for S vector. Now, taking call on both sides of equation 3, we get grad cross E is equal to minus mu del by del T grad cross H. Grad cross E, vector identity formula, grad dot E minus grad square E is equal to minus mu, in place of grad cross H, epsilon del E by del T, or del by del T epsilon del E by del T. That term as 0 under that of condition grad dot E is equal to 0. Minus grad square E is equal to minus mu epsilon del square E by del T square. The term to this side, grad square E minus mu epsilon del square E by del T square. Equation number 5. This one, the wave equation for electric field, which is wave equation for electric field, and that electric field in which type nature? It is time varying electric field. Which one is time varying electric field? Condition in isotropic dielectric medium. Isotropic dielectric medium. Next, expression for S vector, we have to taking call on both sides of equation number 4. Similarly, taking call on both sides of equation 4, we get curl of H grad cross H is equal to epsilon del by del T grad cross E. Using the property of vector identity, grad dot H minus grad square H is equal to epsilon del by del T grad cross E minus mu del S by del T minus mu del S by del T. Grad dot H will be 0 under that condition. Minus grad square H is equal to minus mu epsilon del square H del T square. Rearranging that equation, that term to this side, grad square H minus mu epsilon del square H del T square is equal to 0. Here that equation is equal to 0. Equation number 6, that one is, which is wave equation for magnetic intensity. Magnetic intensity, and the nature of that magnetic intensity is time varying in isotropic dielectric medium. Isotropic dielectric medium. Two wave equations for electric field, wave equation for magnetic field. Now, we compare these two wave equations to the general wave equation. We have to compare to that of general wave equation to relate the idea of velocity. Comparing equation number 5 and equation number 6, and 6 with the general wave equation grad square psi minus 1 by v square del square psi del t square is equal to 0. We have see the psi is a scalar function. In place of psi we can write either E vector or S vector. Comparing to that equation to equation number 5, so we have 1 by v square is equal to epsilon E. Again this equation to that of equation number 6, 1 by v square is equal to under root of 1 by v square is equal to epsilon E. One by v square is equal to mu epsilon, or velocity v is equal to 1 by under root of mu epsilon. This one is the velocity at which that electromagnetic waves propagates through that of isotropic dielectric medium. The expression, this is the expression for the speed of electromagnetic waves in dielectric medium. Here we can using the relation mu, permeability is equal to relative permeability into permeability of free space, and permittivity of that of dielectric medium, that is relative permittivity into permittivity of free space. Therefore V is equal to 1 divided by, in place of mu r mu naught, in place of epsilon r epsilon naught, under root V is equal to 1 divided by, here we can rearrange to that denominator one as mu r epsilon r mu naught epsilon naught under root, or V is equal to 1 divided by mu r epsilon r under root mu naught epsilon naught under root, 1 divided by mu naught epsilon naught under root is equal to C. So V is equal to C divided by mu r epsilon r under root. What we see as here C 1 by mu naught epsilon naught under root, the speed of electromagnetic waves in free space or in vacuum. Hence what we clear from that of expression, as we say relative permeability is greater than 1 and permittivity of that free space is greater than 1, that is relative permittivity, relative permeability and relative permittivity is greater than 1. We have V, that the velocity term is very greater than the speed of light. What it indicating, that is the speed of electromagnetic waves. Speed of electromagnetic waves is the C in that of isotropic medium is less than the speed of electromagnetic waves in free space. Here V is the expression for speed of electromagnetic waves in dielectric medium. That is why we clear in that of expression as the speed of electromagnetic waves in isotropic dielectric is less than the speed of electromagnetic waves in free space. Okay. The speed of electromagnetic waves in dielectric medium is less than that of speed of electromagnetic waves in free space. In free space, the speed of electromagnetic waves is much more as comparison to that of any medium. So, here with the help of this video lecture, we understand the concept of propagation of plane electromagnetic waves through isotropic dielectric medium. These are the conditions for isotropic dielectric medium. By using that conditions, Maxwell's equations are changed. To derive the expression for E vector and S vector, we taking call on both sides. First, we obtain the wave equation for electric field, which is time varying, the condition for isotropic dielectric medium. Next, this is the wave equation for magnetic intensity, that magnetic intensity also time varying in nature in isotropic dielectric medium. And comparing these two equations to the general equation of wave equation, we obtain the speed of electromagnetic waves in that of dielectric medium, and then compare to that of speed of electromagnetic waves in free space. We show that the speed of electromagnetic waves in isotropic dielectric medium is less than that of speed of electromagnetic waves in free space. So, with this useful and informative notes, let me wind up the session. Thank you.